Okay, in this video, I'll be working through some examples from section 2.1. And as I work through the video, there'll be some times that I ask you to pause and look at your checkpoint worksheet and work a few problems on your own. You can find the answers to your checkpoint problems at the end of the section in your textbook. So let's get started. This chapter is about graphs, lines, and inequalities. So we're going to start with graphs, and some of this is going to be review for you. Just go along with it and enjoy the easy assignments. Okay, this is our Cartesian coordinate system graph. And you can see here's a y-axis and an x-axis, which divide this graph into 4 sections. We call those sections quadrants. The quadrants are numbered usually with Roman numerals. This is quadrant 1, 2, 3, and 4. So they go counterclockwise, which may be a little unusual or maybe not what you're used to, but that's how we number our quadrants. When we want to graph points, we usually express the points in terms of an ordered pair and list the x-coordinate first and then the y-coordinate. So let's look at an example of this. In the first example, it says, the table shows the percentage of unemployed workers in the labor force in January of a recent year. So we've got a table there, and I won't copy the whole thing, but I will let you know that the first few entries for 2012, it was 8.3. For 2013, it was 8.0. And then the last entry is for 2017. The entry is 4.8. So looking at these numbers, we know that our x-axis needs to go from 2012 to 2017. So I'm going to move my axes, so I'm only looking at the first quadrant. And particularly in business applications, a lot of times we only need the first quadrant because we're not interested in negative numbers, either for time or money or most of the other quantities that we're talking about. So I'm going to put the y-axis over here. And we'll make this the x-axis. And label those. And I've got numbers from 2012 to 2017. So that's a total of 6 numbers. And I'll just make this first block 2012. And because those numbers are kind of, actually I'm going to leave the 20 off and just make it 12. And I can put a little wiggly line here. That tells me that I didn't start at 0. This is 12, so this would be 2013, this would be 14, and 16. Okay. My other numbers on the y-axis go from 4.8, that's the smallest one, up to the 8.3. So again, I'm going to put a little wiggly line here and just start this at 4. I'm going to do 5, 6, 7. I'm going to make that a little bit lower so that 8's not right at the top. So we'll say we start here at 4, 5, 6, 7, 8. It's important to always remember when I'm choosing the units for my graph that the units have to be uniform. Okay, I can't go from here to here and call this 4 to 5 and then say, well, from 5 to 6 is going to be 2 blocks. If it's 1 block from, or 2 blocks from 4 to 5, then 5 to 6 also needs to be 2 blocks. Okay, you use the numbers in your chart to figure out what to put on your axes, but you generally don't put the numbers from the chart directly to the axes. So let's graph. Our first number, 2012, 8.3. So on 12, I'm going to come up to 8. This would be 8.5, so 8.3 would be about there. Okay, 2013 was 8.0, so here's 2013, 8.0. 2014, 6.6. So on 14, I'm only going to be here. 2015, 5.7. So that's about here. 2016, 4.9. So just below the 5. And then 2017 is 4.8, so just a little bit lower. And there are the points for my graph. Go ahead and work on checkpoint 1. Another thing we want to know when we're working with equations is whether a particular ordered pair is actually a solution to an equation. So let's look at an example of that. Okay, I have this equation, y equals negative 2x plus 3, and I want to know, I've got 2 ordered pairs. The first one is 2, negative 1, and to determine if that's a solution, all I have to do is put the 2 in place of the x and the negative 1 in place of the y and see if I get a true statement. So we're going to have here negative 1 equals negative 2 times 2 plus 3. So working on this side of the equation, negative 2 times 2 is negative 4 plus 3, and that is equal to negative 1, so this is a good solution. Let's try another. This time we'll look at 4, 7. Same procedure. 7 is equal to negative 2 times 4 plus 3. Well, this gives me negative 8 plus 3 is only going to give me negative 5. So this is not a solution. Okay, it didn't give me a true statement. Now I'll go ahead and work on checkpoint number 2. In this example, we're going to graph an equation by constructing a table of values. This is very similar to finding the solution, except we pick numbers that we know are going to be solutions for the equation. So here's an equation. Y equals negative 2x plus 5. And I'm going to make a table of values. And generally I like to have some negative numbers, some positive. So let's start with negative 1, 0, and positive 1. And once I have these values, I can figure out if I need to have some more values to get a better idea of the graph. So if x is negative 1, I would have negative 1 times negative 2. So this would be positive 2 plus 5 is 7. And then if x was 0, I'd have just a 5. And if x was positive 1, I'd have negative 2 plus 5, so that would be 3. And if I make this just a first quadrant graph, then these points are going to fit on it very nicely, except for that negative 1. So I'm going to move my y-axis over just a little bit so I can plot that point. Okay, so my first point is negative 1, 7. So negative 1, 1, 2, 3, 4, 5, 6, 7. There's that point. 0, 5. 1, 2, 3, 4, 5 right here. And 1, 3. So there's 3 points. I really only need 2, but it's nice to have a third one just to confirm that I'm graphing correctly. And now I can connect those to get a graph of that line. Try this on your own and work checkpoint 3. Another way that we can construct a graph is by finding the x and y intercepts. As I said before, we really only need 2 points to construct a linear graph, and often the x and y intercepts are convenient points to use. So let's take a look at this. This time I'm going to have a quadratic equation. And they want me to sketch a graph for this. So to find the y-intercept, the y-intercept means where would I cross the y-axis. And to find that, I'm going to let x equal 0, because if I'm on the y-axis, I know that x is 0. So I've got y equals 0 minus 0 minus 8. So my y-intercept is 0, negative 8. Okay, to find the x-intercept, I'm going to do the same thing in reverse. I'm going to let y equal 0 and then find, in this case, it's going to be 2 values for x because it's quadratic. So let's do that. So now I'm going to have 0 equals x squared minus 2x minus 8. I'm going to have to factor this now. So I'm going to have x minus 4 times x plus 2. So this is going to give me solutions of x equals 4 or x equals negative 2. So those 2 points are 4, 0 and negative 2, 0. Now I'm going to have to move my axes a little bit to get this to fit. I've got that negative 8, so I'm going to put the x-axis all the way at the top of my graph. And since I have one negative and one positive here, I'm going to let the y-axis come straight down the middle here. And now I should be able to graph all these points. 0, negative 8 is going to be right here. 4, 0. 1, 2, 3, 4 is here. And then negative 2, 0 would be over here. These 3 points don't really give me quite enough to graph a parabola, so I'm going to pick some points in between them and graph those as well. So So here's my equation. Y equals x squared minus 2x minus 8. And I had a point here at x equals negative 2. So let's try x equals negative 1. And that's going to give me 1 plus 2 minus 8. So that would be negative 5. I'll put a point here. Now I'm going to try x equals positive 1. So this is going to give me 1 minus 2 minus 8. So total of negative 9. So that point is right here. If I let x equal 2, I'm going to have 4 minus 4 minus 8. So I'm back to negative 8. I'm seeing that there's a little symmetry here. This is probably the vertex. But I'm going to go ahead and do x equals 3 just to be sure. And that's going to give me 9 minus 6 minus 8, which is negative 5. And again, lines up with a point that I had before. Now I have enough to do a pretty good drawing of this parabola. And it's time for another checkpoint. Now we'll look at a different kind of function, a square root equation, and use the same method to construct its graph. So my equation is y equals square root of x plus 2. Okay, now I want to pick some values for x that are going to give me nice whole numbers for y as much as possible. So I'm going to start off with x equals negative 2. If x is negative 2, then y is 0. And then let's try x equals negative 1. Negative 1 plus 2 would give me just 1. So then I would have 1 here. Okay, I'm going to skip over 0 because I don't want to do square root of 2. And I'll go all the way to x equals positive 2. And if x equals positive 2, I've got 2 plus 2, so 4, take the square root, gives me 2. So I can kind of see where my graph is going. Let's get it started. I do have some negative numbers for x, so I'm going to move that y-axis over again. Maybe right about there. And my values for y were all positive, so I can leave the x-axis down here at the bottom. And I've got negative 2, 0, so negative 2, 0 is here. Negative 1, 1 is my next point. And then positive 2, 2 would be here. Okay? If you don't feel like that's enough, you could always put in, let's say x equals 7. 7 plus 2 is 9, and the square root is 3. So I could come over here, and I'd be a little bit off of my graph. But there's another point. So this is my graph. Okay, we've worked through some procedures on basic making of graphs. Now let's look at how we can read graphs. The graphs in the next two examples are on your checkpoint sheet, so I'll ask you to refer to that as we work through them. Newspapers and websites summarize activity of the S&P 500 index in graphical form. The results for the 21 trading days for the month of December 2016 are displayed in the graph. The first coordinate of each point on the graph is the trading day in December, and the second coordinate represents the closing price of the S&P 500 on that day. We have two questions to answer for this graph. The first one, what was the value of the S&P 500 index on day 4 and day 15? And the second question, on which trading days was the value of the index above 2,240? To answer the first question, find 4 on the day axis and draw a line up to the graph. Then draw a line from the graph back to the vertical S&P index axis. The line intersects the axis a little above 2,210, so I estimate the value to be 2,212. Repeat the process for day 15. Here's the line from the day axis to the graph. When I trace back to the vertical axis, I am right between 2,260 and 2,270, so my estimate is 2,265. For part B, I want to find the days the index is above 2,240. I draw a line at 2,240 and see that the day 5 point is just above the line and the day 21 point is just below it. So the index is above 2,240 from day 5 to day 20. Now work the checkpoint problem number 5. Let's look at another example. Monthly revenue and costs for the Webster Cell Phone Company are determined by the number T of phones produced and sold, as shown in the chart. Question A. How many phones should be produced each month if the company is to make a profit? And question B. Is it more profitable to make 40,000 or 44,000 phones? Profit is defined as revenue minus cost, so the company makes a profit anytime the revenue line is above the cost line. This begins at 12,000 phones and ends at 48,000 phones. So the company makes a profit at any production level between 12,000 and 48,000 phones. To answer part B, calculate the profit for the given production levels. At 40,000, these are the data points we need. Subtracting, we get a profit of 1.7 million. Repeat the process for production of 44,000 phones. At this level, the profit is only 1 million, so there is more profit at the 40,000 phone level. This could be due to the need for overtime or more equipment to achieve the higher production level, eating into profits. Now work checkpoint problem number 6. This concludes this lesson. You should now be ready to work assignment number 1 in Math Lab.